Hello and welcome to this video. In this video we will learn about problem number 201 to 210 of complex numbers. So as I always say in my video that when I'm stating the problem we should pause the video and try to solve the problem yourself. Only if you cannot solve the problem yourself then look at the solution. So without further ado, let's get started. Problem 201 says that two different non-parallel lines cut the circle mod z is equal to r at points a, b, c, d respectively. Prove that these two lines meet at point given by a inverse plus b inverse plus c inverse plus d inverse divided by a inverse, b inverse, c inverse, d inverse. So there are two cases of two such lines meeting. One would be that they meet outside, another is that they meet inside the circle. So let P be represented by Z and ABCD represent points ABCD. So clearly PAB will be collinear and PCD will be collinear. So from the equation of straight line we know that Z bar 1, A bar 1 and B bar 1, that is this determinant would be 0. So we solve this determinant. Note that we have not yet discussed determinants, so it's an advanced problem. You have to know both determinants and complex number to solve this. So by expanding this determinant, we will arrive at z into a bar minus b bar minus z bar into a minus b plus ab bar minus a bar b is equal to 0. And similarly, because PCD is also collinear, we will have z c bar minus d bar minus z bar c minus d plus cd bar minus c bar d. Now we want to find z, not z bar, so it's best we eliminate z bar. By eliminating z bar, we arrive at z into a bar minus b bar into c minus d minus z c bar minus d bar into a minus b is equal to cd bar minus c bar d into a minus b minus ab bar minus a bar b into c minus d. So once we have this, we also know that because a, b, c, d lie on the circle, so mod of a will be equal to mod of b equal to mod of c is equal to mod of d is equal to r. So we have a square is equal to b square is equal to c square is equal to d square is equal to r square. This relation we can arrive at simply by taking origin at center. So once we have this, we can further say that a bar is equal to b bar is equal to c bar is equal to d bar is equal to r square, and we have a bar is equal to r square by a and so on. Now we have found a bar, b bar, c bar, d bar. So we substitute in the previous equation we have obtained, we arrive at this equation. And now it's just a matter of solving for z and we will have the desired answer. Problem 202 says that if z is equal to 2 plus t plus I square root of 3 minus t square where t is real and t square less than 3, show that mod of z plus 1 by z minus 1 is independent of t. Also show that the locus of point z for different values of t is a circle and find its center and radius. So we have z plus 1 by z minus 1 is equal to 3 plus t plus I square root of 3 minus t square divided by 1 plus t plus I square root of 3 minus t square. So we find square of the mod of this fraction, and you can see we have solved it. We have arrived at 3, which is independent of t. That is the first part of the problem. Now we let z is equal to x plus iy. So by comparing the coefficients, we have x is equal to t plus 2. Not comparing the coefficient, comparing the real and imaginary parts, we have x is equal to t plus 2 and y is equal to square root of 3 minus t square. So from here we get that t is equal to x minus 2. We substitute here. And then we square both sides. We arrive at x minus 2 whole square plus y square is equal to 3, which is equation of circle with center at 2, 0 and radius square root of 3, which is the second part of the problem. Question number 203 says that let z1, z2, z3 be three non-zero complex numbers such that z1, z2 is not equal to 1, z1 is equal to a, z2 is equal to b, and mod z is equal to c. These are mod Z1, mod Z2. Sorry for the mistake. So mod Z1 is equal to A, mod Z2 is equal to B, and mod Z3 is equal to C. Now we let ABC, BCA, CAB, this determinant is 0. Then we have to show that argument of Z3 by Z2 is equal to argument of Z3 minus Z1 by Z2 minus Z1 whole square. So since we are given that these three are non-zero complex number, we have from this determinant a cube plus b cube plus c cube minus 3abc is equal to 0. Now, since these are non-zero and Z2 is these are non-zero, so a plus b plus c will not be equal to 0. Okay. And since this is not equal to 0, so the second part must be equal to 0. That is a square plus b square plus c square minus ab minus bc minus ca. This should be equal to 0. And from here, we infer that a is equal to b is equal to c. Now, this can happen if O is origin. It is one example. O is an origin which is circumcenter of this triangle such that this is the case. It's down here. That is ABC lie at the circumference of the circumcircle. So once we have this diagram, the angle made by the chord BC at O will be double than the angle made by the chord BC at A. Okay. So from here, the angle made by BC at O is BOC, that is equal to argument of Z3 by Z2, will be twice the angle made at circumference or perimeter, that is 2BAC, which is equal to argument Z3 minus Z1 by Z2 minus Z1 square. Problem 204 says that P is such a point that on a circle with OP as a diameter, 2 points Q and R are taken such that angle POQ is equal to angle QOR is equal to theta if O is the origin and PQR are represented by complex number Z1, Z2, Z3 respectively. Show that Z2 square cos 2 theta is equal to Z1, Z3 cos square theta. Now here O is the origin, P is the point Z1, we have Q and R. Clearly, OP will make angle 90 degree at these 2 points. Okay, that is at Q and R. And we are given that angle POQ is theta and QOR is theta. Alright. So from this, we see that Z2, that is this guy, is equal to OQ, that is this guy, divided by OP into Z1 e to the power I theta. Okay. This comes from the rotation. So if you try to rotate this guy, it will rotate this way. It will be slightly bigger than this. That is why we have Z1 e to the power I theta, but the extra component would be OQ by OP, right? So Z2 would be slightly less. So OQ being smaller is in the numerator and OP is in the denominator because it is a larger quantity. So we see that Z2 is equal to Z1 e to the power I theta cos theta. Similarly, Z3 would be Z1 e to the power I2 theta cos 2 theta. So from these two equations, we have Z2 square is equal to Z1 square cos square theta e to the power I2 theta. And so we have Z2 square cos 2 theta is equal to Z1 Z3 cos square theta, which is what we needed to prove. Find the equation in complex variables of all the circles which are orthogonal to mod Z is equal to 1 and mod Z minus 1 is equal to 4. So we have two circles, that is mod Z is equal to 1, that is x square plus y square minus 1 is equal to 0. And the second circle is x square minus 2x plus y square minus 15 is equal to 0. So we let the circles, family of circles which will cut these two orthogonally is x square plus y square plus 2gx plus 2fy plus c is equal to 0. So if you look at this equation, and since it cuts this guy, so one of the equations would be that this g is 0 and f is also 0, because at the point where they meet, the solution of these two equations should represent the point. So at that point, the g would be 0 and f would be 0 and c would be minus 1. sorry, c would be 1. Right? Now, for these two, we have g is equal to 7 from this equation. So the family of circles which will come is x square plus y square plus 14x plus 2fy plus 1 is equal to 0. Now, if you want to replace this as a complex number, it would be z plus 7 plus if mod of that is equal to square root of 48 plus f. Problem 200 says that find the real values of the parameter t for which there is at least one complex number z is equal to x plus iy satisfying the condition mod z plus 3 is equal to t square minus 2it plus 6 and then equality z minus 3 root 3 I less than t square. So mod z plus 3 is equal to t square minus 2t plus 6 is equation of a circle having center at minus 3 comma 0. Let's call this point A. Okay, and the radius t square minus 2t plus 6. Now we have let A here and R1 here. Okay, so in this case z will lie on the circle. The second case where mod z minus 3 root 3 I is less than t square implies z lies on the interior of the circle having this center and radius t square. We call this point B and R2 t square. Now if you see AB is 6 and R2 minus R1 is 2t minus 3. Okay, you subtract R2 minus R1, you get 2t minus 3. Okay, now clearly if the circles are disjoint or they touch each other, solution won't be possible because here z lies inside the circle and here z lies on the circle. So if they are disjoint or touching each other, z will have no solution. So there are two possible cases. First case is when t is greater than 3 and R2 is t is greater than 3, that is R2 greater than R1. So here if t is greater than 3, this will become a positive quantity. That means R2 is greater than R1. So in this case, 1z is possible if AB less than R1 plus R2. Okay. So the distance between the centers, these two centers A and B, is less than the radius, that is the two circles intersect. So we substitute the value of AB and R1, R2, we get the value of T. So we have T, from this equation, we have T is either less than 0, but here T is greater than 3, so it is invalid. The second case is T greater than 1. So from t greater than 1 and t greater than 3, we find that the solution which will satisfy the inequality is t is greater than 3 and less than infinity. Now the second case would be when t is less than equal to 3, that is R1 greater than R2. Alright. So if t is less than 3, clearly this will become a negative quantity and R1 will be greater than R2. So in this case, z would be possible if modulus of R1 minus R2 is less than equal to AB less than R1 plus R2. Again, we solve and we find the case that t should be greater than 1 or t should be less than 0. So from these two, we combine the solution and we arrive at the result that t can be between 1 and infinity. Question 207 says that if A, B, C and D are real values and AD greater than BC, so that imaginary parts of the complex number Z and AZ plus B by CZ plus D have the same sign. So we let Z is equal to X plus IY and we have AZ plus B by CZ plus D is equal to this much, right? So we rationalize and the bottom becomes 6 plus d whole square plus c square y square, which is immaterial because it would be positive. So from the numerator, we find the imaginary part of this az plus b by cz plus d, which is on solving, when we solve it, it becomes ady minus bcy and the denominator is positive. So you see here, if we take y common, we will get AD minus BC, but AD is greater than BC. Okay, so AD minus BC would be positive. The sign of this whole imaginary part would be same as sign of y. So from this we deduce that the Sign of imaginary part of Z and Az plus B by Cz plus D have the same sign. Problem 208 says that if Z1 is equal to x1 plus I by 1 and Z2 is equal to x2 plus I by 2, and along with these two given conditions, we have Z1 is equal to I Z2 plus 1 by Z2 minus 1, then we have to prove that x1 square plus y1 square minus x1 is equal to x2 square plus y2 square plus 2x2 minus 2y2 plus 1 by x2 minus 1 whole square plus y2 square. So we have Z1 is equal to much. So we substitute the values of Z1 and Z2. We have x1 plus I y1 is equal to minus y2 plus I x2 plus 1 x2 minus 1 plus I y2. We rationalize with the denominator. That is, we multiply and divide with x2 minus 1 plus I y2. So from this and this, we compare the real and imaginary parts. So we have x1 is equal to minus y2 into x2 minus 1 minus x2 plus 1 y2 divided by the same, is equal to minus 2x2 y2 by the denominator, and y1 would be x2 square minus 1 minus y2 square by x2 minus 1 whole square plus y2 square. Now we substitute this x1 and y1 for x1 square plus y1 square minus x1, and we will have the desired result. Problem 209 says that simplify the following. Cos 3 theta minus I sin 3 theta to the power 6 into sin theta minus I cos theta to the power 3 divided by cos 2 theta plus I sin 2 theta to the power 5. So cos theta minus I sin 3 cos 3 theta minus I sin 3 theta is equal to e to the power minus I 3 theta. And if we raise that to the power 6, it will become e to the power minus I 18 theta. Now cos 2 theta plus I sin 2 theta is e to the power I 2 theta whole to the power 5. Now this will become e to the power I 10 theta. This 2 theta should have been appropriately typed. Okay, anyway. Now sin theta minus I cos theta to the power 3 we have to compute. So what we do is we take out minus I. Once we take out minus I, it becomes cos theta plus I sin theta. So we raise to the power 3 here. So this becomes I into e to the power I 3 theta. This should not have any theta. This should be 3 theta. Once we have this, we substitute these 3 here and we arrive at I dot e to the power minus I 25 theta. This is nothing but sine 25 theta plus I cos 25 theta. Problem 210 says that find all complex numbers such that z square plus mod z is equal to 0. This is a very straightforward problem. We take z is equal to x plus iy. Our equation becomes x square minus y square plus 2xy plus x square plus y square. Now we equate imaginary parts. We have 2xy is equal to 0. That means either x is equal to 0 or y is equal to 0. So we take x is equal to 0. Then what happens is the real part becomes minus y square plus square root of y square. Okay? That essentially means y to the power 4 plus y square is equal to 0. Okay, that implies y is equal to 0 or y is equal to plus minus I. You can substitute these values in here to verify. So if you put y is equal to 0, it becomes 0. You take plus I, so this becomes plus 1 and this becomes minus 1. Hang on. So there is some problem. So we have this. How do we arrive at this? So you square this and you take this to the right side and square this. This should be minus y square. There is some calculation mistake here. This should be y to the power 4 minus y square is equal to 0. That would give plus minus 1, not I. This should be 1. So now you try to substitute this. You substitute plus 1. This becomes minus 1 and this remains plus 1. So it will become 0. And then we substitute minus 1. This will become minus 1. This will become plus 1. So this should be plus this should be 1, not I. Now if y is equal to 0, then we substitute again. We get x square plus square root of x square equal to 0. Now since x is real, again if you look at this equation, it will have no solution because you bring it to the right side, you will have x to the power 4. Let's try to find out. It may be wrong again. So x to the power 4, and then right side will become x squared. You take it again, so x squared into 1 minus x squared. So this will also give you the same solution, same set of solution. But know this, that when you square left side and right side, extra solutions may come. So you again substitute it back, try to solve this. So for example, we take plus minus, there are three solutions we arrive at, 0 and plus minus 1. But if we substitute plus 1 or minus 1 in this, then we find that it is not equal to 0. It will become 2 in both the cases. So the only solution in this case would be 0. At least there is no calculation mistake here. This is correct. Here it should be 1. So now y being 1, the z will become 0 and plus minus 3. So with this, we come to the end of this video. I hope that you have found this video useful and informative. If so, please subscribe to the channel and like the video, because like other videos, when I say that, it motivates me to make more such videos, because how YouTube algorithm works, if you like and subscribe to the channel, then it will increase the reach of the video. That will help other students like you. So thanks a lot for watching. Have a nice day.